Okay, now week 6 contents. From this week, we will use these 3 weeks to study kinetic equation of motion. Last week, we touched a little bit about kinetics of a rigid body. But in last week, we only discussed mass moment of inertia. When we studied kinematics from week 1 to week 5, no force was involved. When we study kinetics, we should know from now, force will be involved. In this week, we will study how to draw free body diagram of rigid bodies, and we will learn the general expression of equations of motion for rigid bodies. And then in this week, we will use equations of motion for rigid bodies to solve problems of translational motion. Please note we are learning planar kinetics. So that means all problems will be 2D. A coordinate system is necessary for our study, and the coordinate system can be fixed or translate with constant velocity, but this coordinate system cannot rotate. Let's see 3 motions when a constant force is applied. So firstly, let's look at translation. Okay, this is the constant force, and in this case, this rigid body undergoes translation. Now, fixed axis rotation when a constant force is applied. And the third one will be general plane motion. Let's have a look. Okay, so we will use equations of motion for rigid bodies to solve problems of translation, of fixed axis rotation, and problems of general plane motion. And in this week, we only deal with translation problems. Equations of motion have 2 components. They are translational component and rotational component. And here, please don't get confused. We are talking about translational component and rotational component instead of translational motion or rotation motion. Whatever translation, rotation about a fixed axis or general plane motion, the equation of motion always has 2 components, translational and rotational components. Firstly, let's look at the translational component. The equation is actually the second law of Newton. We can express this equation using vector form or using scalar form, because we are dealing with planar kinetics. So the problem will be 2D problem. So here you can see only x and y components. Look at this diagram. And here, the rigid body may undergo translation, rotation about a fixed axis, or general plane motion. On the left side, this is free body diagram. And in this diagram, all external forces, including couple moment, M2, M1, they are couple moments, need to be indicated. The acting point of weight force is the mass center point G. Other external forces include F1, F2, F3, and F4. And here there is the coordinate system. This coordinate system x, y, its origin is at point P. On the right side, this is called kinetic diagram. And in this kinetic diagram, all accelerations need to be indicated, including angular acceleration alpha and the acceleration of the mass center point G here, AGX and AGY. External forces on the left side in this free body diagram result in the accelerations on the right side in this kinetic diagram. If we only focus on translation component, here what we can get is the sum of all the external forces acting on this rigid body should be equal to the body's mass times the acceleration of its mass center point G, and here expressed using x component and y component of AG. Now we focus on rotational component only. In this equation, on the left side, we have moments generated by all external forces. We can select point P to calculate all moments. On the right side, we have so-called kinetic moment. This includes MMI, IG times angular acceleration alpha, and kinetic moment calculated using the calculation of mass center point G. Here, this item. On the left side, the first item means the moment generated by F1, F2, F3, and F4. The second item means the couple moment, here M1 and M2. And this equation can be simplified like this. And in this expression here, on the left side, That means the resultant moment about point P due to all external forces. And on the right side, that means kinetic moment about point P. And here, mk, k means kinetic, mk means kinetic moment. We can select a point P to do the calculation, but in many cases, we actually can select mass center point G to calculate the moments. If we select a point G, then we will set point G as the origin of the coordinate system xy. Okay, now you will see, if we set point G as the origin of the coordinate system, then in the last slide, in the equation, x bar and y bar, these two will become 0. Then what will happen? We will get an equation like this. The resultant moment about point G should be equal to Ig alpha. This rotation component tells us the resultant moment about the mass center point G, here, point G, due to all the external forces, should be equal to the moment of initial about mass center point G times the angular acceleration of this body, alpha. Combining the translational and rotational components, we can obtain the equation of motion for general application. This is the general expression. And here, in this slide, we show this general expression of the equation of motion in vector form. And here, we can also show this general expression of equation of motion for rigid body using scalar form. So here, these two translational components. And here, because this is planar kinetics, so we have only x and y, two components. If it's 3D, we should have another component along z direction. And here, this one, rotational component. And for this rotational component, the calculation can be about point P, or it can be about mass center point G. Next, we will use the equation of motion for a rigid body to deal with the problems of three motions: translation, rotation about a fixed axis, and general plane motion. But in this week, we only deal with translation. Okay, now for translation. And we already know for translation, if a rigid body undergoes only translation, then every point on this rigid body must have the same acceleration. So, the mass center point G at this point, the acceleration AG here should be equal to the acceleration of any other points on this rigid body. Because this is translation, so the angular acceleration alpha must be 0. In a xy coordinate system, the translation component should be like this. And actually, for translation, rotation about a fixed axis, or general plane motion, for all these three motions, the translation component is always the same. For rotational component, it will depend on what point is selected for calculation. If mass center point G is selected, then it must be 0. Why? Because we know the resultant moments about point G must be equal to Ig alpha. But here, this is a translation, so alpha is 0, so it must be 0. If point A instead of point G is selected, then what will happen? You will find if A is selected for calculating rotational component, it will be like this. This time, it's not a 0. In particle dynamics, we know when the path of motion of a particle is known, normal and tangential coordinates can be adopted. The direction perpendicular to normal tangential plane is binormal direction. Binormal direction is not useful in planar rigid body kinetics. For convenience, normal tangential coordinate system may be adopted for a problem of curvilinear translation or rotation about fixed axis. And here you can see we use normal tangential coordinate system to deal with a problem of curvilinear translation. Because we are using normal tangential coordinate system, so this time for translation component, it has two components. One is n, normal, one is t, tangential. For rotational component, as similar as before, it can be about the mass center point G, because this is translation, curvilinear translation, so it must be 0. But it can also be about another point, for example, point B. Okay, now let's see two applications. One is a tractor, and this tractor raises the load. And here, the crate will undergo curvilinear translation if the forks do not rotate. Okay, watch a video. The second application is about a trailer. And for this application, let's watch another video.
Truck drivers see some amazing things on our roads and highways. Tonight, the latest dashcam video to emerge is a reminder of how careful you need to be while towing a caravan.
Consider this a lesson in how not to overtake. A caravan teetering out of control.
Once it starts fishtailing like that, I think you're done and dusted. You're going to crash.
And resulting in carnage.
Oh, it could have been fatal. Quite easily could have been fatal.
This accident took place on Monday on the M1 just outside of Newcastle. The frightening moments all captured on truck driver Paul's dash cam.
There's a bow wave of air pushed in front of the truck and it goes out to the sides, and when the caravan went past, it just sort of moved the caravan a bit. The guy swerved in and then off it went. It just fishtailed and multiplied and crashed.
Thankfully, the man driving the mobile home was not injured, but it could have been much worse.
So yeah, I think if you'd kept going straight ahead a bit further, Ali, the whole thing would not have happened. It's just him cutting across from the right lane too early.
Peter Barnwell is a motoring writer for Cars Guide. He says you can't just hook up a trailer behind a car and drive it straight away.
Because it's a completely different discipline. You know, you've got it's longer, it weighs twice as much, it's articulated in the middle, so it bends all the time. You know, you've got to make sure everything is in your favour. You've got to check the brakes on both vehicles.
We see it on our roads so often. Drivers not recognising the degree of difficulty added when a caravan is attached. Take this four-wheel drive towing a caravan at the Iluka turnoff on the Pacific Highway. It's already skidding out of control before it even reaches the intersection. Unbelievably, the victims of this crash also escaped injury. Russell White is from Driver Safety Australia. He says if you're driving with a caravan attached to your vehicle, there are a number of safety precautions that you should be taking.
Moderating your pace, making sure that you're not driving too excessively for both the tow vehicle and the trailer unit itself. If you can, also start to make sure that you've got the correct sort of sway or the correct couplings for the vehicle and the trailer as well to try and prevent that trailer sway. But one of the other things you can do is just make sure your vehicle is loaded correctly.
If you're driving a newer vehicle, there's a chance you may already have the new trailer sway control technology, which uses the electronic brain of the car to moderate any potential sway in the trailer by applying the brakes.
And if it detects any sort of movement in the back through the anti-lock braking system, it'll apply the brakes or cut the power to the wheels to sort of compensate for any sway. It's really clever, but that's only on relatively new cars.
It's about driving to suit conditions, about understanding that it's not a normal car situation, and just being that little bit more progressive and being extra careful to just make sure that you're not doing something that's going to upset the balance of the car even further.
Next, we will use equation of motion for a rigid body to solve some problems of translation. And before we solve this problem, just highlight one thing. Free body diagram and the kinetic diagram must be presented in all the solutions. Because the direction of friction force can be involved in a lot of problems. So here, I will discuss how to determine the direction of friction force. between a rolling rigid body and the contact surface. Look at this diagram. Here, there's a vehicle. Front wheel, rear wheel. In this vehicle, the rear wheel must be a driving wheel, and the front wheel should be a driven wheel. Okay, now for this wheel A, the driving wheel, how to determine the direction of friction force between this wheel and this contact surface, the ground. The method here has two steps. So firstly, we assume no friction between this wheel and the contact surface, and then observe the resulting motion. In the second step, we can determine the friction force must act on the body opposing the motion of the body. So what does this mean? Let's have a look for this wheel A. So firstly, we assume no friction between this wheel and the ground. If no friction, what will happen? This is the driving wheel. If no friction between this wheel and the ground, what will happen? The wheel will rotate about this axis without moving forward, isn't it? So it will be a rotation about a fixed axis. Then the direction of the motion of the contact point on this wheel will be to left side, because here the angular acceleration, angular velocity, this is clockwise. So the motion of the contact point on this wheel here should be to left side. Then the direction of friction force at this contact point must be opposite. So it should be to right side. This is FA. Okay, now for wheel B is the driven wheel. If no friction between this wheel B and the contact surface, what will happen? This wheel must be moving like a block, moving forward like a block. So this means it will be a translation. There will be no friction. If no friction, there will be no rotation if no friction between this wheel and the ground. Okay, now the direction of the motion of the contact point on this wheel B will be to right side. Then the direction of the friction force at this contact point must be opposite, so it should be to left side. Okay, now a problem. This is example 2. And here there's a motor cycle, and we know its mass is 125 kilo. The mass center point of this motorcycle is G1. And here there's a rider. Its mass is 35 kilo, and the mass center point is here, is G2. The task here is to determine the minimum coefficient of static friction force between the wheels and the pavement in order for the rider to do a wheelie. What does this mean? It means the front wheel will be off the ground, like this. For this purpose, a suitable acceleration is necessary. And here we are taught the mass of the wheels can be neglected, and we assume the front wheel is free to roll. We can define this problem, and we know the rider and the motorcycle, they are undergoing rectilinear translation. Because the front wheel is off the ground, so this means the reaction force at front wheel must be 0. And next, we can draw diagrams. We are going to use equation of motion for a rigid body to solve the problem. So we will need to present free body diagram and kinetic diagram. On the left side, this is a free body diagram, and on the right side, this is a kinetic diagram. And we use a conventional coordinate system, x, y, and here we define counterclockwise is the positive rotation direction. Okay, in this free body diagram, at G1, the mass center point of the motorcycle, we have weight force Wm. Wm means the weight force of the motorcycle. At point G2, the mass center point of the rider, we have Wr, and Wr means the weight force of the rider. At the contact point between the rear wheel and the ground, we have reaction force Mb, and we have friction force Fb. This is the driving wheel, so Fb is direction to right side. This one here, this is front wheel, this one is driving wheel. If this front wheel is not off the ground, then we will have reaction force Na and friction force Fa. For Fa, its direction should be to left side. Because this wheel is off the road, so actually Na and Fa, both of these two, should be 0. In kinetic diagram, at mass center point G1 of the motorcycle, we have mmAg1. mm means the mass of this motorcycle. At G2, we have mrAg2. mr means the mass of the rider. Okay, now we can list all already known parameters, mr, mm, and we already know NA and FA, these two should be 0. For AG1 and AG2, because no relative motion between the rider and the motorcycle, so AG1 and AG2 should be equal. And actually, AG1Y and AG2Y should be 0. Okay, we don't know FB, NB, and we don't know the static friction coefficient. We don't know AG1X, AG2X, they are equal, so actually we don't know AGX. AGX, in this one here, G means the mass center point of this system, consisting of the motorcycle and the rider. But for the location of point G, we don't know. Okay, we assume all these unknown parameters are positive. I normally assume all unknown parameters are positive in my solution. And this can give me some convenience. Okay, equations. For translational component, we have these two equations. For rotational component, the calculation can be about point G and can be about another point. In this problem here, we can select B, point B. Point B is the contact point between the rear wheel and the ground. And here, is it possible for us to select the mass center point G of this system consisting the rider and motorcycle to calculate the rotational component? Actually, we can, but we must know the location of this mass center point G. In this problem here, it's not necessary to know this. So we are not going to use point G to do our calculation. We will use point B to calculate the rotational component. Next, the solution. Along x direction, we have two external forces, FB, FA. We assume FB positive, FA we know it should be 0. On the right side, we have MR AG2X and MM AG1X. So actually, these two, AG2X and AG1X, they should be equal to AGX. Along Y direction, we have NA, NB, WR, WM. NA is 0. NB, we assume is positive. WR, WM, both of them downward, so they should be negative. Along y direction, the acceleration is 0. So on the right side, you can see it's 0. So from here, you can see we actually can work out NB directly. Now for the rotational component, the calculation will be about point B. So that's the calculation. For resultant moments generated by all external forces, we have to consider WR, WM, and NA. Again, here, NA, we already know it's 0. For WR and WM, the moment of these two about point B, the moment should be negative. On the right side of this equation, it should be kinetic moment. For MR, AG2x, for this one, about point B, the kinetic moment is negative. And for MMAG1x, is also negative. Okay, from equation 2, we can get NB directly. Then substitute this NB into equation 3. We can work out AG, the acceleration at the mass center point G of this system. This one is positive. Then we substitute this AGX to equation 1. We can work out FB, and this FB is the minimum required FB. Okay, now using FB divided by the reaction force at point B, NB, we can work out the minimum required static friction coefficient. This should be 0.912. And here, NB positive, AG positive, FB positive. That means in the beginning, we assume all these three are positive. The assumption was okay. Okay, please note, row without slipping will result in static friction force. Row without slipping will result in kinetic friction force. Now let's look at one video to show coefficient of friction.
We are going to analyze how the coefficients of static and kinetic friction affect the amount of force used to make an object move. Here we have a force sensor. As you can see, as we pull on the string that is attached to the hook on the sensor, the computer reads off how much force is being applied to the sensor. We will use this to analyze the amount of force required to move carts with different coefficients of friction.
Here we have a cart with added weight on it. This cart is attached to the force sensor through the string. As you can see, we have different carts with different surfaces on the bottom, so we can analyze the graphs of the different coefficients of friction.
So let's look at our free body diagram first. We have our weight acting down on the object, our normal force acting up on the object, and we have our force acting horizontally to one direction and our friction force acting on the opposite direction. Now, through Newton's second law, we can derive that our normal is going to be equal to our weight. So our friction force equation is going to be equal to mu times mg. Now, if we look at our first part of the graph of our friction force with respect to time, all the way up to the peak, we have our static friction, which is going to be less than or equal to our mu s times mg. And when we reach the peak, our maximum static friction is going to equal our mu s times mg.
Please note here, mu s is the static friction coefficient. Static friction coefficient can only let me know the maximum available static friction force. But the actual static friction force may be equal to this maximum available static friction force and may be less than this maximum available static friction force.
Afterwards refers to our kinetic friction, and this is going to be equal to our mu k times mg. Now, if we solve for mu s and mu k, we have our mu s equal to our maximum static friction over mg, and our mu k is going to be equal to our kinetic friction over mg.
For kinetic friction force, it's different. If you know mu k, kinetic friction coefficient, then use mu k. You can work out the actual kinetic friction force.
Here we have our cork surface cart. The total weight of the cart is 10.78 newtons. As we pull it, we can see the amount of force generated on the graph below. Our peak force value is 5.858 newtons, so the coefficient of static friction is 0.543. The average moving force is 4.786 newtons, so the coefficient of kinetic friction is 0.444. We can do the same experiment with the felt and plastic surfaces. For the felt, the static coefficient of friction is 0.228 and the kinetic coefficient of friction is 0.208. For the plastic, the static coefficient of friction is 0.178 and the kinetic coefficient of friction is 0.127. As you can see, it requires more force to make a cart start to move than it does to keep it moving. It also depends on the surface of the cart. As the roughness of the surface increases, so do the coefficients of friction and the applied force. This allows us to conclude that the force acting on the carts is proportional to the coefficients of friction and that the coefficient of static friction is larger than the coefficient of kinetic friction.
Okay, this problem, example 5. And this is the interesting problem. And here you can see a uniform 50 kilo crate rest on a horizontal surface. And we already know the kinetic friction coefficient between this rigid body and the surface is 0.2. And here the task is to determine the acceleration if a force of point P is applied to this crate. So firstly, we need to define this problem. What can happen if we have an external force acting at this point, so how many possibilities? You probably think the only possibility is after acting this external force P at this point, this correct will be moving forward. It will be a translation. Yes, this is correct, but just one possibility. Another possibility here is if the acting force, acting point of the force is here, and if the current is very heavy, and or if the friction between this current and the surface is very high, what might happen? When you push this current here, probably this current will not get a translation to move forward, but get a rotation, a tip. A rotation about this corner point. So actually there are two possibilities. Okay, so we define this problem and we can see two possibilities. One is rectilinear translation and another one is rotation about a fixed axis through point A. A is the corner point. So firstly, we need to assume one possibility, then do our calculation, and finally using the final answer to verify our assumption. And here we assume possibility 1, rectilinear translation. Okay, now diagram. This is a free body diagram, and at this point we have external force P. At mass center point G we have weight force W, and at this point, point C, we have reaction force NC and friction force F. Friction force here to left side. Okay, now a question. Why this reaction force NC should be here, C should be here, but not in the middle? The reason is this external force P. Because this external force P has a tendency to result in a tip of this correct rotating about this corner point A. So this will be able to move the acting point of reaction force N from C prime, the middle point, to C. The distance from C prime to C at this moment is unknown. We assume it's X. Okay, now kinetic diagram. And here, because this is rectilinear translation problem, so here we only have MAGX and AGY must be 0. and we use a very conventional coordinate system x, y. Assume set counterclockwise as the positive rotation direction. Okay, we know P, we know M, we know mu K. We don't know AGX, we don't know NC. We assume these two are positive, we don't know X. Okay, now equation of motion for a rigid body. The first two, translation component. The third one, rotational component. For this problem, we can select point G, the mass center point, to do the calculation. And that's calculation along X direction, along Y direction, rotational component about point G. Finally, we can work out NC, AGX, and X. And here you can see NC is positive, AGX is positive, so that means in the beginning, the assumed positive direction of NC and AGX, they were correct. And X is 0.467. Okay, that's the final answer, but it's not the end. It's not the end of this solution because we made an assumption. Now we have to verify this assumption. So how to do this verification? Okay, we will use X. X, you can see, is 0.467. And we already know from this corner point to this corner point, the length of the bottom side of this crate is 1 meter. So this means from C prime to A should be 0.5. And X is the distance from C prime to C. It's 0.467 meter. So this is in the range. So this means the answer should be correct. The assumption is valid. And here, if you worked out an X and this X is larger than 0.5 or X is negative, then that means our assumption was incorrect. The correct should be ongoing rotation about the fixed axis through point A, the corner point, but not a rectilinear translation. This problem, example 4 here. This problem, the only thing I like to highlight is for this kind of problem, because this is the curvilinear translation, so we can use normal tangential coordinate system. Of course, you also can use XY coordinate system, but using this example just to show you, for curvilinear translation, it might be convenient to use normal tangential coordinate system. And here shows you an example. And you may work out your solution by yourself and then compare your solution with the solution provided in this slide.